Greetings! In this video, we'll explore how to use UWAL's built-in SDF text rendering feature and create some shader effects with it. A while ago, inspired by Astiapin's WebGL fonts project and Alfredx's portfolio website, I tried to recreate the ripple effect on his landing page in raw WebGL 2. The result, even though it required around 1,500 lines of code, was pretty satisfying and funny to play with, so I decided to reproduce it once again with UWAL and WebGPU. We have a lot of work to do, so without further ado, let's get started. Once again, let's start by creating an empty project using vite and bun. We open a terminal window and run bun create vite at latest. Call it UWAL ripple effect and choose vanilla and JavaScript. Let's then cd into the folder. Add UWAL with bun add UWAL command. Open Visual Studio Code and start the dev server by running bun run dev. Let's clean up some files we won't need. Optionally add VS Code settings and edit the git ignore file. In the index.html file, we can then change the title, add some initial styling, and create a canvas element. In the main.js file, we can remove vite's boilerplate code, import UWAL and some UTIL classes, grab a reference to our canvas, and instantiate a rendering pipeline. We will need some UTIL functions to load JSON files and textures, so let's add those as well. Speaking of font files, let's add them to the project. Import at the top of our program and load them all together by using promise.all method. UWAL requires 2 files per font type, one being the font atlas texture and the second its characters data in JSON format. Since we'll be using 2 different fonts, we'll need a total of 4 files. Link to the tool that allows us to generate these files from a TTF font file will be in the video description below. We will need 2 global references to our text, a title and a subtitle. So let's add them along with a flag indicating that all textures required for this program are loaded, which we will need in the window resize event handler. Speaking of which, let's add this function and set canvas size to the whole viewport of the window. The rest will be done once all our textures have been loaded, so we're good here for now. Once our textures are loaded, we can fetch shader module and fragments entry from static method SDF text get fragment state params. It will play a bigger role later. So for now, let's move to the vertex buffer layout that at the moment has to be explicitly created using render create vertex buffer layout method. This step will be further automated in future releases in order to retrieve it from the same SDF text method above, but for now it has to be created manually. Now we're finally ready to create the text pipeline by calling render.create pipeline with all required parameters. To keep things simple now, let's render to a white background, so we create a color attachment to do that. Title will be blue and the subtitle color will be black. Background color defaults to white, so we're ready to create text instances. We'll set different textures to each text and write some strings to the screen. As last thing here, let's space out the 2 strings a bit honoring device pixel ratio and render the text. The first render method won't need to submit the command buffer since both texts are using the same pipeline, so we can render them with the same draw call. Last thing left to do is to handle the resize event. Let's set the loaded flag to true, call resize method on the title and the subtitle, and render again the scene. Looking good. Now, if we comment out the white background and change subtitles color to white, there's an issue with what's called subpixel rendering, because as mentioned before, text background color defaults to white. We can fix this by creating a new color value matching the one on the background of the page and pass it to the SDF text constructor. Looking good again. But there's a better way to do it. We need to change a few small things, but it's going to be worth it. First thing first, let's require dual source blending feature right before instantiating a rendering pipeline. Unfortunately, at the time of recording this video, it supported only in Edge and Chrome browsers, so I'll leave a link to Can I Use page. Later we won't depend on this feature, but it's cool to see how it can ease things a bit in this context. We'll also need to retrieve fragment target object from the same SDF text static method and use it in our pipeline. Now we can safely remove background color settings and play around with the color attachment value, since we're not depending on it anymore. To make things a little more interesting, let's use a background image instead of a boring monotone color. We start by adding it to the public directory, importing it into the program, and loading it along with other textures. The goal here is to use this image as a background size cover in CSS, so we need to create a small UWAL function to make it expand accordingly. This getBackgroundOffset function will calculate offsets along the X and Y axes, and we will store them in a GPU buffer before sending them to the shader. Let's also create a reference to this background image that will be useful later in the resize handler. A background uniform to store our GPU buffer and layout and instantiate a new texture builder. Now, in the resolve callback, we can create a new GPU texture using texture.copyImage to texture method. We won't be using mipmaps, so let's set this flag to false since they are created by default. We need to create a new rendering pipeline with UWAL's quad shader and a custom one. We'll write in a bit. Let's also set up a background uniform buffer, get offset values. Write them into it, and finally, for resize purposes, let's save these objects into our background uniform. Now in the render function, we can comment out the text rendering for now, create a bind group and its entries, set it to the newly created pipeline, and render a full-screen quad with 6 vertices. As mentioned earlier, in the resize handler, we need to recalculate background offset again and update the corresponding GPU buffer. Back at the top of the file, let's import UWAL shaders and a custom one. Speaking of which, let's create a file and call it result.wixel. We can start with a vertex output that will be returning vertex position as usual and background coordinates. We've set our bind group to have a texture sampler in the first position, a background texture at the second, and the offset buffer at the third, so we need to keep this bindings order here as well. Since we're using UWAL's quad shader, we can call getQuadCoord function to calculate vertex position and use it along with the background offset to calculate and return background coordinates as well. Finally, in the fragment shader, let's simply sample our background texture using background coordinates from the vertex output. Wow, that was a lot of work to match one simple line of CSS. Let's now merge the two pipelines, shall we? We will render our text to a texture, so we can mix it with the background and manipulate both later. So first thing first, let's declare a text texture and ask for a BGRA8U norm storage feature, because if available, this will be the preferred canvas and texture format, so we need to have it among required device features. Let's also create references to the text pipeline and to the result, which is basically the last step of this program, an output to the screen. We can grab a reference to the text pipeline and remove the color attachment, since we'll need a transparent texture to apply on top of the image background. And since we're here, how about adding some transparency to our text as well? Now we can create a storage texture for our title and subtitle by calling texture that creates storage texture with a render attachment, since we also want to see it in the result pipeline. Speaking of the result pipeline, let's grab a reference to it here as well. In the render function, we use the text pipeline first and render to a texture view, which is our storage texture. We don't submit the command buffer until the end, so we render subtitle with false flag as well, end and destroy the current pass. Next up, we use the result pipeline and add our text storage texture to its bind group entries. We need to reset renderer's texture view, and we're ready to go. Now in the resize handler, we simply need to destroy the text texture and recreate it again in order for it to be of the updated screen size. Back in our shader, we add a new vertex output entry and a new group binding. We update vertex function return value accordingly. And in the fragment function, we can finally use text chord values to sample our text texture, and using its alpha value, mix it with the background image and return the color. Sadly, this is not enough. As you can see, the text is not blended nicely with the background image anymore. Looks like we need to replace dual source blending with a custom solution at this point. Let's comment it out from the required features and import a new shader file we'll create shortly. Since we're using two different pipelines, we need to duplicate our background uniform for the texture pipeline. Let's call it texture uniform. Remove the fragment entry, since we'll not be checking for the dual source blending anymore, but using the default fragment function and add our custom shader to the text pipeline. We create a new uniform buffer called texture offset, which is going to be exactly the same as the background offset in the result pipeline. Title and subtitle are both using the same pipeline, so we can use either of them to add a new bind group to this pipeline, which will have index 1. We will need a default texture sampler, our offset values, and the background texture again. And let's not forget to update our texture uniform buffer in the resize handler. Now we can override text pipeline's default fragment shader. Let's create a file we've already imported and add bind group entries in the same order as we described in the JavaScript file. Default fragment entry function name is fragment, and it accepts a struct called text vertex output that will give us access to some font values. Now, let's tweak background texture offset values a bit and use them to calculate proper UV coordinates to sample this texture. Just like in the result shader, the Y coordinate has to be inverted here as well. The whole idea here is that instead of using a solid background color for the subpixel rendering, like the text pipeline does by default, we'll sample the texture on the background to know exactly each pixel's color, and use that value to mix it with the font's color. Default text shader hasn't gone anywhere, so we can use a function it provides called getSubPixelCoverage to retrieve a value we can use as a weight to linearly interpolate between pixels on the background and the solid, semi-transparent color of the font. Looking pretty good, but now to the fun part. Once again, we want to create a new pipeline and render its output to a texture we can then provide as an input to the result pipeline. Let's start by adding a new image we'll use in this pipeline. The idea here is to create a distortion texture from several shapes called waves that will all share the same material with the same map texture. To help us with this, we can use UWAL shape class for the geometry part of the wave. We'll then create a new shader file to be used as a material and import a newly added image for this material. We'll save mouse coordinates in an array and instance up to 128 waves, changing their size. So let's create some constants for all these features. We'll also need references to the wave's texture, to the shape geometry and mouse movement timeout ID, as well as the last render timestamp, whether the mouse is currently moving and the current wave index. The array of waves instances will contain some useful information like the current rotation angle, scale, and the alpha value. Now to the utility functions. The first one is to obtain a random angle in radians. The second one will create a bitmap image without any color space conversion or mipmaps, since we'll be using the raw red channel of this texture. We then create a shape geometry as a simple quad and set its position to the screen center. By default, shapes do not use any textures, just plain colors. So we can create and add a new bind group at index 1 to this shape and set its entries to the just created texture and a sampler with linear filter to sample it. Next utility function will update wave instances every frame. We'll calculate the current delta frame and a couple useful variables, and when the mouse is actually being moved, we need to update the wave index and set its initial values firstly in the typed array and then in the corresponding GPU buffer. We can now iterate through all the wave instances and update their settings in order to scale and fade out each one as time goes by. Again, we firstly update the typed array and then write it to the GPU buffer. Since each shape update will reset vertex buffers in the render pipeline, we need to add them again here. A little uncomfortable, but not a big deal. Let's update the last render timestamp and return shape vertices count that we'll need to pass to the submit method. A simple move handler will track if the mouse has been moved since the last frame with a good enough math, normalize and save its coordinates. Now, let's create the waves pipeline. To do that, we need to create a new shader module using default vertex shader, and a custom one we'll write a bit later. For a target state, we'll need a color blend component with a source factor of source alpha and a destination factor of 1. For the default vertex shader, position layout is required, but the already mentioned wave buffer and wave layout are part of custom updates, so let's create those as well. Let's not forget that these are instances of a vertex buffer, and we have 128 of them. Now we're ready to create the waves pipeline and the typed array we're updating at each animation frame call. Let's load our ripple texture into this program and create a wave shape. Before we're ready to render, we still need to create a reference to our waves texture, add the mouse move event listener, and create a render loop using request animation frame function. Speaking of rendering, the waves pipeline should be the first to be used. We render again to a storage texture, waves texture this time, by setting again renderer's texture view. Since our update waves function returns the amount of vertices in a wave shape, we can pass it to the render call along with the amount of wave instances in our program. We then need to end the current pass and reset the state before setting the next pipeline. Waves texture will be the third entry in the result pipeline. Let's not forget about actually looping render calls and the resize handler where we need to destroy waves texture, reset shape's default position to the center of the screen, and recreate again our wave storage texture with new screen dimensions. Finally, we can now update our shaders. We start by creating a new shader we're already using in the waves pipeline called wave. This is basically a replacement for the default shape shader we need in order to use a texture we've loaded instead of just any plain color. Vertex function will output the position as usual, UV chords to sample the texture, and an alpha value that was passed from JavaScript. We got two bindings here in group at index 1, a sampler and a 2D texture. We will need a UWAL function to rotate this very texture around its center by some amount at each frame. So let's create and call it rotateOutputUV. As the name suggests, it will accept a pair of UV coordinates and an angle by which they need to be rotated. For this operation, a cosine and a sine of this angle are required. So let's extract them and, as mentioned, set the pivot at quad center. We return a new set of UV coordinates ready to be used to sample the wave texture. In the main vertex function, which accepts all the data defined in the vertex state layout, we initialize an output struct and calculate position coordinates using offset coordinates and get vertex clip space function from default shape vertex shader that, as you may remember, was also included in this shader module. Clip space coordinates are also useful to calculate UV values, applying the correct aspect ratio and the scale of the wave. Lastly, we rotate these UV values using the function defined above and return them along with an alpha value updated at each frame in the vertex buffer of this pipeline. The fragment shader in this pipeline will be as simple as accepting vertex's output struct, sampling wave's texture using UV coordinates, and returning its color with alpha channel multiplied by the alpha value from the vertex buffer. Last thing left to do at this stage is to update the result shader. In order to see just the waves pipeline at work, let's create a constant called frameBuffer at the top of this file. It will be our debug flag we can enable to switch between the complete output and the one with just the waves pipeline. Next, don't forget to add waves texture as a new entry in the bind group and update indexes of the background texture and its offset. Finally, we can sample the wave's texture, get any of its color channels since it's grayscale, and just output to the screen the result if frameBuffer flag is set to true. Looking sharp, isn't it? At last, we're ready to use the newly created frameBuffer texture to distort all other pixels on the screen. In order to achieve that, we'll need a new constant. Let's call it tau and make its value equal to twice of pi. Since we're here, let's toggle our debug flag to false so the actual result will be rendered. Next up, we need a distort function accepting current UV coordinates in input along with a distortion factor coming from our wave's texture as a color channel value. An angle called theta can now be calculated so we can extract its direction, use it along with the distortion factor and some strength value to distort input UVs and return a new value. Since we've got two input textures that have to be distorted, we call this function twice with corresponding UV vectors in input and save the results as new pairs of UV coordinates. And as the very last step, we replace original chords with new ones when sampling our background and text textures. That's it. Now we have a nice ripple effect that can be easily customized and funny to play with on some landing page. Once again, feel free to try UWAL by yourself and fork this program on GitHub. I'll leave both links in the description of this video so you can check the source code and the live version. Thanks for watching. Cheers!